No, no.
Motion. All right. All right, we're going to get started. Thanks for coming, everybody. Since the mid-1980s, one of the criticisms, a set of criticisms that's been leveled at multi-layer neural network models is that they're not biologically plausible. And at the heart of the criticism is backpropagation, the algorithm that is used to adjust all of the synaptic strengths deep inside of these model neural networks. And maybe in 2014 or so, I started to hear some rumors of biologically plausible variants or alternatives to backpropagation. And the first paper that I read on it was in probably early 2015 that I read it, and the first author was Timothy Lillicrap, our speaker today. So when I've been thinking about trying to bring speakers here who can try to bridge the gap between neuroscience and deep learning that's revolutionizing artificial intelligence today, I thought immediately of trying to bring him here. It turns out that it's not an accident that he has this interest in neuroscience. He was an undergrad at the University of Toronto and majored in cognitive science and AI. Was a graduate student at Queen's University in Kingston, Ontario, where he worked with Stephen Scott on models of motor control, making contact with data from monkeys and humans. He was a postdoc at Oxford with Colin Ackerman, where I think he did this backpropagation work where I first learned about him. And then since maybe it was 2014 or thereabouts, he joined DeepMind in London. And there, of course, he's been involved in the deep reinforcement learning, but also maintains this interest in synapses and dendrites. So I've been looking forward to hearing from and meeting Timothy for months now. And so here's our opportunity. Please. Welcome.
Hi. I think I've got the mic on. We'll see. Good. Okay. Hi. So I've been interested in this question about whether deep learning might have anything to tell us about the brain for a long time. And I just to sort of situate things briefly, I often kind of find myself wondering, what is it going to look like? What is it going to look like when we boil down sort of the principles for at least systems neuroscience? And I think actually, for me, I think usually of these three, maybe four things. And that is that I want to know what the network architectures are. I want to know what the loss functions are, the things that the system is trying to optimize. And I want to understand the learning rules that are pushing the system to sort of pursue those loss functions. And I'll probably need to understand the environment as well in a certain sense if I'm really going to understand how this whole thing works. And I think this is, in some sense, there's something left out here, and I don't know if I'll have time to get into it. But this is what we're doing a lot of the time when we're doing sort of practical machine learning. These are the things that we actually write down. These are the things that actually guide us. And I think, therefore, it might be good to aim at understanding these components. There's been some really cool work recently that I think most of the people in the room will be aware of from DiCarlo's lab, Dan Yanemans, and from Nicholas Kriegeskort's lab, where they've looked at taking big deep networks that have been trained to do things like categorize images, and then compare representations to, say, monkeys, their visual systems. And the kind of remarkable thing is that off-the-shelf models showed better representational matches than models that people had been working on for decades to try and emulate those systems, right? To try and capture what's going on in those systems. Now, I actually think that the representational matches in and of themselves are kind of a bit besides the point. I think that they're exciting to the extent that they let us zero in on what the loss functions and network architectures are. And indeed, some of those groups have begun to do that. So what they've begun to do is sort of say, if I vary the loss function, or if I vary the network architecture, and I rerun this optimization, how close is the representational match now? And so that can let me do inference on those things that I think are sort of at fundamental. I'm going to talk today about this thing primarily, this third one primarily, which is learning rules, and it's the one that I've been kind of obsessed with for a long time. And that's where I'll sort of focus, but I think there's really interesting work going on in sort of tying deep learning to the brain on these other fronts as well. So, okay. I want to start for a moment and talk about the credit assignment problem and the credit assignment problem in deep networks. So in networks that are chained and serial, where say there's sensory information that comes in, and you need to process that through multiple stages to produce sensible outputs. And when you need to do that, anytime you need to do that, you really adjustments to these synapses say need to pay attention in some sense to what happens downstream. If you don't know what happens downstream, ultimately it's impossible to really know how you should adjust these synapses to do better at some loss function that lives further downstream. And so that's crucial when you're representing big, deep, complicated functions. Okay, the solution in artificial neural networks is really clear and dead simple, and that is that people use backprop, and they use it everywhere. And I want to spend a couple moments just sort of reflecting on this. When I say they use it everywhere, I really kind of mean that now. So people often associate backprop with supervised learning, right? So this is sort of where I have labels, I have sort of some inputs, and I have some labels, and I want to adjust the network to make sure I produce those labels better in the future. But actually, backprop shows up in all of the best sort of unsupervised and reinforcement learning algorithms that we use now. So it really is sort of endemic to the field. And without it, basically none of the solutions that have worked on hard problems recently, none of them would work in essence. Just so I have some sense of the audience, how many people have coded a backprop network by hand in their life? Okay. So is that fair to say that's like an eighth of the? Okay. So it's a little less than I had imagined. So I mean, we'll see if I can sell you on it, but I would say, it's worth going and writing one of these things once if you're in neuroscience. I think I suspect these things will become increasingly important. We'll see, as a hypothesis. So with that in mind, I'm gonna take certain things a bit slower, and some people may be a little bored, but there we are. Okay. So I just want to spend another moment thinking about talking about backprop as it is in machine learning, and say the following. So often people will say as well that, okay, well, there's various reasons why people will say, does backprop have anything to do with the brain? One of the other issues besides the supervised issue is that backprop learning is notoriously slow, and humans and animals learn quickly. This is another issue that's pointed out. But I want to say that there's all sorts of work going on in the field to sort of contend with these issues. And an important point is that backprop does not drop away. That's not going anywhere. So here's some work that we did, but many people have done work in this field where, in this sort of area, where the idea is to, you're going to see images come in, and you're going to have to learn to categorize them, and you're going to have to do this on the fly with very few examples. So you're only going to get maybe at most 5 examples of an image, and you want to be able to classify it. And actually, it's quite. It turns out that if you furnish a neural network with a memory bank system that it can read and write to, as you might with a hippocampus, these kinds of tasks are really tractable, and in fact work quite nicely. So there's a whole sort of meta-learning field where people play around with involving memories to do these sorts of things. Notably, if you do that, so this is some results where you've introduced this external memory. When you do that, even for sort of hard problems, you can see that by the time a network has seen 10 instances of an image, so 10 instances of a new class that it's never seen before, these things can perform sort of a near ceiling. And so these systems can learn quickly. They're not just slow. And again, the backprop part that supported the actual sort of feature production does not drop away. You still want to contend with that. There's also stuff going on where we're beginning to do things like introduce planning. So here's some work we've done where you're sort of controlling these systems and doing them from pixels alone. And you can combine basically recurrent predictive models. So this is a model in which we're sort of producing predictions of the future, and then subsequently using those models to plan. And when you do that, a lot of the complaints, again, about model-free reinforcement learning that have come up recently, which is that they're very data hungry. They need, potentially millions of frames. A lot of those issues drop away, so you can get massive reductions in data requirements. Again, the essential system we're working with, the thing that makes it all possible, is doing backprop in big networks. Okay, so that's sort of some of the objections on the more the machine learning front. I now want to kind of go on and talk about what's sort of connecting this to neuroscience, and we're going to ramp up into that more and more. The key feature of deep learning and using backprop, and I think that what has been missing from a lot of neuroscience models is this sort of, let's think about the loss function, let's think about how to drive that loss function down, do well on it. When we've studied things like spike time dependent plasticity, Hebbian learning, the issue is that these are largely, so say a learning rule like this is largely detached from the behavior and what we're trying to optimize. And so, if I, for example, if I have a system like this where I have some spiking in these neurons, and I would say strengthen the synapse based on sort of correspondence, pre and post synaptic spiking, the issue is that if I don't understand what's going to go downstream, what B's firing is going to be used for downstream, then I have no idea if I should have actually strengthened that or reduced it, right? And that's sort of fundamental. So okay, so here is backprop in one slide, effectively. And actually, there's a small mistake on here, but we're not going to get into it. But if you're an expert, there is a small mistake in here. Basically, backprop just says compute the chain rule for this thing, right? So basically, it says here was a target that I had for some outputs. Compute an error between these nodes and that target, and then use the chain rule to compute an update for this synapse. So W naught here is that sort of input connectivity matrix, and so you're going to say what's the derivative of the loss with respect to this these input weights, and basically it's just application of the chain rule. That is it in some sense, but it has pretty profound consequences. And I'll unpack this expression a little bit in a moment. So here we go. So this is sort of from the other end, why the sort of complaints about why is backprop not biologically plausible. And I want to first of all start by saying it absolutely isn't. In its sort of basic form, it is absolutely not biologically plausible, and most sensible people will agree on that. Okay. Now, I'm going to run down some of the reasons that have been historically given for that. Some of these reasons, I think, really have fallen away. So that is, like, they used to be big complaints, and now I think of them as kind of secondary. There are still major issues to resolve, but some of these really have fallen away. So the first one, okay, so let's look at this thing. So this thing says to compute this, the changes for this, the earlier set of weights, what I need is an error that comes down. I need the transpose of the downstream weight matrices, and that's going to be sort of crucial. I need to compute with that. I need the derivatives of the local activation functions. This actually I think is not such a big deal, but we can talk about it in a moment. And I need the inputs to those neurons. But fine. Okay, so this first issue, errors, I think actually has been a major sticking point for people in the past. People would often say, quite rightly, where would the brain get labels? So where would the brain get targets to sort of update things toward? One of the things that I think we appreciate much more now is that there's all sorts of places to get errors from, labels, targets from, and that don't have to be provided by like an external supervisor who says, that's a cat, right? So one of the most common would be to say, predict what's going to happen in the next couple time steps, right? So to predict what when I put these inputs into my muscles, what's going to happen? Things like this. And from that, you can derive an error term and do all kinds of learning. So there's all kinds of unsupervised learning that goes on in that mode. The other bit to say on that front is that we work a lot now with reinforcement learning algorithms, for which again there is no target. The only thing that you get is a bit of reward once in a while, and you either produce your own targets, in a sense, using algorithms like Q-learning, or you do policy gradient. And in both cases, there's no target. No one's giving you a target, and yet you discover where to move with these algorithms. And notably, again, you're still sort of bottoming out in using backprop. So this other one is one that I'll come back to a whole bunch in this talk, and that is this transpose of the downstream weights. And it's worth resting on this for a moment. This really is crazy. This would say in essence that somehow these synapses, these neurons, would know very precisely about the connectivity strengths of these synapses. And we'll see that again in a moment. I'll look at that again in a moment. This one, the derivative of the activation function, the local activation function, this is really, I think, actually pretty simple, and people have worried about it, but it's not really that big a deal. Then I think this is another one that I won't get into too much in this talk, but this remains an issue in some sense. I think there's something fundamental here, which is that in these backprop networks, there are typically separated out forward and backward passes. So you'll run a forward pass and then pause for a moment, run a backward pass, and then use these to make updates to your weights and to get better with respect to some loss function. And that really is an issue. Okay, so why is this an issue? Great. So lots of things to say about this, but maybe the sort of the simplest thing to say is that it really doesn't look like the brain has such sort of phases that you can identify like this, where you could really see what looks like a forward pass and then some sort of pause and then a backward pass. There's also issues with timings that go on with these things when you get into the nitty gritty. So if you have a network that's made up of more layers than this, you need ways to make sure that the timing of the feedback signals that arrive here are precise enough, or that there's memory of the variables that sort of were ongoing earlier that can be matched up. So there are real timing issues, and when you try and instantiate these things in more biological networks, they start biting you. But it's a good question. Again, I'm gonna focus on other issues, maybe just because some of them are actually bigger in a sense. Okay, so then what I often have in my head is this, and because I still haven't told you in some sense, like why backprop, and this picture is sort of beginning to get at it, and that is, so you should think that there really are a spectrum of credit assignment algorithms. There's lots of ways that I could try and make decisions about how to make updates to my synapses deep in my network. And one of the things you could do are various reinforcement learning algorithms, which look like weight perturbation or activity perturbation. And basically, the way these things work is this. You would say, have a small bit of noise that occurs at your synapse or occurs at a node in your network, and correlate that small bit of noise with changes in the error that your network makes. So basically, in the simplest case, you can imagine just taking your network, passing something up through it, and getting it to label something. Then do exactly that same procedure, but in one of the units, you add a little bit of noise and pass back up through and see if it got a little closer or a little further from the label that you wanted it to produce. You use that correlation to make a weight update and basically say if things got better, then do more of that. Basically increase the weight that I had added a bit of noise on and things got better. Increase it. At the other end of the spectrum are things like, so that in some sense you're measuring then dependencies between error and injections of small amounts of noise in your network. Backprop actually computes, so it computes a weight change direction, which basically says, if I move in this direction on all of my synapses, I will get better, and this is in fact the steepest direction of descent. Okay. Now the ramifications, though, on this spectrum, it really have to be, we have to dig into this for a moment. There's something that really important that happens with these two algorithms as you make networks bigger and deeper. And that is that these things that live in this space, basically become less and less effective. So they just get worse and worse and worse as I scale these network sizes and the problem complexity. And there's complex interactions between those things that we don't totally appreciate, but we know that as a basic fact. And that's one of the reasons why, in essence, a lot of the big results like ImageNet and so on, even though this is hypothetically a way that you could train these networks, no one has ever trained a successful ImageNet network using these simple methods. And that's worth sort of having in mind. Okay. So this is sort of like some very quick sort of a sense of what would happen for a very simple problem like MNIST. MNIST is kind of this character recognition thing, which is kind of like the Drosophila of machine learning, people often say. And so this is accuracy on this axis. This is the number of epochs of training that have gone on. So these blue curves are backprop. And the blue curves are backprop. And notably here, we're increasing the number of neurons. And the interesting thing that happens here, you'll see, is that actually backprop got faster when I increased the number of neurons. And actually, this is sort of like a widespread phenomenon that people are beginning to appreciate more, which is that even bigger networks turns out to be even better. And weirdly enough, so this is really an aside, there's some recent work which is sort of pointing to the fact that actually even bigger networks suffer less from overfitting. So they're like, you know, if you just keep over-parameterizing, you actually have less problems with overfitting. But that's kind of an aside. There's some weird stuff down that road. The main point that I wanted to make here is that these algorithms like node perturbation, weight perturbation, the sort of simple ideas that we would have about how to make changes in a network naively, they fare poorly, and they tend to fare worse with network size. So here's 100 nodes for node perturbation, 200, 400. So it actually gets worse. Here, there's a little bit of sloppiness in the weight perturbation results, but effectively that result will hold. Things will just get worse for you as you increase the size of these. Okay, so that's why for a machine learner, there's no, I have no trouble convincing a machine learner that you need to do something that looks a bit like computing a gradient. It may not have to look exactly like it, but you had better sit somewhere here, so in this spectrum of learning rules, if you want to solve hard problems. So how you convince a neuroscientist that Cortex is doing something, is learning via something like backprop. So I'm not sure if I can really answer this question, but this is something that I often try, a little bit of an argument that I try to go through. So first of all, I want to say, what do I mean by something like backprop? It's worth trying to be a little bit precise about this. I'm not going to be very precise, but I'll be a little bit precise. And what I mean by something like backprop is that learning is achieved across multiple layers by sending detailed information from neurons closer to the output back to earlier layers to help compute their synaptic updates. So there's a huge space of algorithms that live sort of in this statement. But in essence, it means that there has to be sort of rich, detailed feedback coming from later regions to earlier regions, and that rich, detailed feedback be guiding weight updates. So just to contrast it and relate some of this to some of the things we often think about with reinforcement learning in the brain, which I want to say, we understand lots about, and I'm not saying it doesn't go on, but something that would not count as detailed information would be like a single scalar delivery of dopamine across cortex. This is not enough, and that's very similar in some sense to these kinds of learning algorithms, if you like. Okay, right. So with that provisional definition in mind, here's an argument that I like to run through a bit, which is that look, everyone I think would accept this number one. That is feedback connection cortex are ubiquitous, and they can modify the spiking of neurons in earlier layers. I think probably uncontentious. Okay, number two, plasticity in forward connecting synapses driven by pre and post-synaptic spiking, e.g., it could be STDP-like phenomena. And in some sense then, thus feedback connections will modify learning at forward connecting synapses. It's just like, in some sense, a fact. Now, you could think maybe that's just epiphenomenal, right? I mean, maybe it does nothing useful. But probably a more sensible thing to think is that it's integral to a good learning algorithm. Okay, I just wanted to comment on this because I think, as I said, it's absolutely clear that reinforcement style learning is going on in the brain, and I just want to make very clear that I'm not saying that it doesn't. I'm saying that these things probably need to work in conjunction, and they can indeed work in conjunction. In reinforcement learning, very quickly, in AI, we write down this kind of thing where you have a neural network that produces, say, an action given some input state, and this action is this action distribution is, say, maybe a probability distribution from which you sample your actions. The important thing to say is that, for example, in policy gradient learning, where you've kind of unfolded things over time, you've taken actions on the environment, got some rewards back. At the end of the day, when you make a policy gradient update, this piece can decompose, decomposes into two parts. There's the part where you're kind of taking an action in a relatively low dimensional space, where you want to, you have in some sense you have no other recourse but to do reinforcement learning, right? Because the environment is not something that lives internal to you, so you need to estimate some things. But then the other part, you can just use backprop. So that is basically saying, I took this action. The reinforcement learning can say, well, actually, probably I should have taken this action instead. But then from that point back through the network, you can compute exactly what the synapses should be, the synaptic changes should have been to elicit those kinds of actions more in future. Okay. Right, so now I'm gonna kind of shift gears a little and get into some specifics work on this stuff. Can I just have a sense of what time it is? Okay, I have half an hour. All right, so I'm gonna focus now on this issue, which actually, this number 2 issue, the transpose of the downstream weights. This problem actually has a name. It was named by Grossberg. When in an article where he was extolling the various problems with backprop and basically saying, in some sense, this is why backprop has nothing to do with the brain. He called this the weight transport problem. So that it was actually a big enough issue that it was given a name. And that is, again, just to remind you, you would need the following situation. So that is, when you have these forward neurons, these forward connecting synapses, you would need a feedback pathway which precisely mirrors this backward pathway in order to deliver the correct error information to this neuron for it to update its synapses, right? And so that's the reason it's called weight transport, in essence, is that the information about the synapse would have to be precisely transported to here, to another place in the brain. And this does look crazy. Okay. So, in I think actually probably in 2012, when we sort of first saw this, this was the paper that was mentioned at the beginning. I was playing around with backprop networks and looking at maybe potentially more biologically plausible ones, and stumbled upon something pretty strange, and that is the following. So, this is a basic backprop network where the weight transpose is being used to take error near the output and carry it back to the hidden layers. And I was playing with algorithms that would, say, learn these weights, and discovered that actually, we'll see some variants on this, but discovered actually that if you replace this matrix, which in some sense is a precise copy of W, a flipped precise copy of that matrix at every time step, with a random matrix, that actually learning worked pretty well, at least for reasonable sized networks and reasonable sized problems. So just to give you a sense of that, this is a simple linear learning problem. So you're just learning to emulate some linear function, so pretty simple. But importantly here, this dark gray line is a reinforcement learning algorithm that's been actually pretty well tuned in this case. So it'll get there. It'll just happen sort of somewhere out here. The black here is backprop, and the green here is this algorithm that we called feedback alignment, which was replacing that backward weight matrix with a fixed random one. So something where you really would not need to transport any information. You just instantiate that matrix and then just go. Now, this should be utterly surprising. It is bizarre, and we'll see there are definitely caveats to this, which I'll show you in a moment. But it's important. There are network dynamics at play here, which we still don't deeply understand. Although there are several proofs that have emerged since, which shed light on some aspects of it. The important thing to understand. So this is I'm going to show you in this plot. This is a measure over time, over learning time, of the angle between what backprop computed as the direction to move in for these neurons. So that's like an angle the backprop said you move in, and the angle that feedback alignment told you to move in. And they do indeed, at the beginning, they set it about 90 degrees, which is basically backprop told you to move this way, feedback alignment told you to move that way. So just totally orthogonal. But very quickly, over time, that angle drops and stays reasonably low, and certainly low enough that you're able to move down the loss landscape much more effectively than you would with reinforcement learning. So this is strange. I think that I'll show you there really are some issues with this simple algorithm feedback alignment, which I'll highlight shortly. I think that the thing to really take away, though, is that these issues that people have pointed to really may have solutions if we go looking, right? So that is the biological implausibilities which are evident in backprop. I think we can, if we sort of take it as a goal, we can unpick a lot of those. That's maybe the thing to take away from it. Just to show you very quickly. This is a little bit harder. This is this is an MNIST, the Drosophila, if you like, of machine learning. And so here is, again, backprop in black and feedback alignment in green. Many people say, like, why the hell is this working better than backprop? It's just worth saying, MNIST really is more of an overfitting game. So if you have a bit of regularization, you can tend to do better. This is the test set. And so in fact, feedback alignment does a bit of regularization. We know now. So that's why you tend to do a little better on the test set. Really, there's not much to be made of it. Similar thing happens with the angles here. The angles of the directions that are sort of recommended by these two learning algorithms. And a similar thing happens if we go and look at the synapses. So you can kind of pick up these neurons, look at the strengths of the weights coming into them, track those over time, and these align as well. Okay, I told you that we don't understand deeply why this happens, and it's indeed true. But I can give you an intuitive pictorial story that you can play out with some other kind of cool diagrams. So, how on earth does this happen? How is this even possible at all? The story looks kind of like this. So there's information that lives in B, this B matrix. It's a bit funny. It was just randomly sampled and fixed, but there's information that lives there. As you begin doing your normal updates here and here, that information moves into these synaptic strengths. At that point, that information then starts showing up in these neurons. And from there, because they're in those neurons, and because the weight updates for W involve those activities, then you have transfer of that information into W. At that point, then there starts to be some alignment between W and B, and that allows effective error flow through this. That is, even though B hasn't changed, W has changed in some sense with respect to B, and now, because it's a little more aligned with B, B becomes a reasonable transducer of error back down the network. Yeah. So very weird, but kind of an interesting. I think the high level lesson is the one to take away from it. Okay, another thing that has happened, and I think this is important, as we've begun to sort of pick away at biological plausibility issues for powerful deep learning algorithms, is that we've moved from sort of notions of neurons which look like this. So that is, our model of a neuron might be that it's got a single compartment, it's a point process, and that basically feed-forward information and feedback information all converges into the same place. It's basically just everyone is injecting voltage into this guy, and that's it, right? And when you sit down and try and build machine learning algorithms that are at once effective and obey this kind of constraint, you find yourself tied into all sorts of knots. And one of the things I want to say that has been really cool about the interplay of, I think, neuroscience, more recent neuroscience and deep learning, is that by moving to more realistic neuronal models, so ones, for example, where you have feedback that can arrive into different portions of neurons, where than what you might want to call feed forward, where you can have interneurons that can control different compartments of a neuron, and where you could say have interplay that's controlled again by other factors between different compartments of a neuron. All of these pieces actually make it easier to go and write down machine learning algorithms which don't tie you into knots while you try and obey constraints. So to give you some notion here, one of the things that has been I think completely mysterious in some sense in the past is like, look, if feedback is supposed to in some sense maybe have a differential effect on this neuron. That is, maybe it carries information about how to make updates here rather than just sort of like being a feature, then it's very hard to do that if you just think that everyone's just dumping voltage into the same compartment, right? So anyway, the high-level lesson is that more realistic neural models are letting us play with algorithmic variations in really interesting ways. We spent a bit of time doing this with some collaborators where we said, okay, well, if we allow ourselves sort of some dendritic compartmentalization, say having feedback delivered into some apical dendrite, can we produce more interesting learning algorithms? And again, the high-level point would be, I think, yes, we can. So that is, we can get deep learning to work in contexts where we're doing integrate and fire, we're doing spiking, more realistic compartments, and it actually helps us. So the data that's coming in from the neuroscience side is actually helping rather than hindering us, essentially because people just had ridiculously oversimplified versions of what the neuroscience was capable of what neurons were capable of. So for the rest of the talk, I'm going to talk about this issue, which is kind of coming from the other direction. So I think that there are people who are going to do better versions of this kind of thing, which is the sort of let's get inspired bottom up from the neuroscience and make sure we're matching the constraints. I've been kind of obsessed on the other side with this issue, with this question, and that is, do existing more biologically plausible learning algorithms scale up to solve hard credit assignment problems? And that is, so people have begun proposing alternatives, but we need to check that they actually work, and sort of stay on that. So for the next little bit of work that I'm going to talk about, I'm gonna sort of lay out a couple of these constraints, mention a few of them, and really pass over a bunch. The main one that I'm going to talk about is this no weight transport issue, which is what we've gone over a few times. There's some other ones which we'll touch on the way, which are things like no weight tying. So most convolutional networks use another form of weight transport, which is that for every neuron in a convolutional map, they all share their input weights, which is very weird, and it's not something that, in some sense, it's another form of weight transport. It would be as if the neuron next to me and I just had a way of telling each other our weights and our weight updates. Really kind of crazy. There's also this question about feedback of signed errors, which I won't get into too much, but there's, I think, some questions about how feedback signals could carry signed information, which really seems quite crucial in backprop networks, and I think we don't understand that well enough. So then there's a whole host of other ones that I'm not going to get into, things like whether you use continuous rate-based signals rather than spiking. Do you violate Dale's law, local activation derivatives, and this business of separate forward and feedback pathways? And yeah, your personal complaint here. Right, and really, no joke. That people will come and find me and they'll tell me that, there's no way the brain can do anything like backprop because of and just fill this in. So we'll see. I think I want to just give the impression that we can make progress, and actually, it's really going to be coming from both ends where we'll hopefully get somewhere. So so I talked about feedback alignment, which really completely gets rid of the issue of weight transport. It does send errors backwards, so it does use signed error information, which is maybe tricky, but I guess I think for the moment, I've been happy to say, and will say from this point on, what could you do even if you do send signed error information? Can you even live without weight transport at all? There's another interesting class of algorithms around target propagation, which are, I think, kind of neat, and they actually do get around this issue of sending signed error information. And they work very roughly like this. So that is, instead of having a backward pathway which you use to send error gradients, what you do is you use a backward pathway to make predictions about what the lower layer ought to be. So that is, you would say, learn this inverse. So you would learn an inverse function for your forward path. And then from that inverse, you can basically plug in a target here and get a target at the lower layer. So that is basically, if you said 5 here, but you should have said 3, if you've learned a reasonable inverse, then you can literally take that target at this higher layer, push it back down through the layer and get a target for the lower layer. And those targets don't have to be signed. They can just be unsigned. And then you compute per layer an error. Right? So this target propagation kind of assumes perfect inverses, but there's an interesting algorithm from Lee and Yoshua Bengio's group where they introduce this idea of difference target propagation, which is a little more involved, but it has a way of accounting for imperfections in those backward inverses. And effectively what that means is that you have a learning rule not only for your forward weights, which you learn to use to learn this function, say, but you also have a learning rule for your backward weights. So you have a bunch of backward weights and you have a learning rule that operates on those as well. And that can be local and relatively easy to use. So what as I said, I'm kind of interested in the moment in kind of keeping us honest from the machine learning end, which is when we propose these new algorithms that might be more biologically plausible, do they in fact work? So we've run some experiments now. So mostly people in the past have run on things like MNIST and CIFAR, MNIST and SVHN, these data sets which are relatively small in machine learning terms and relatively simple. And I am absolutely guilty of this, at least until this work. And so what we said is, let's push further. Let's make sure we actually run on larger networks, where those larger networks really are required for data sets like CIFAR and ImageNet, which are the places where we really have seen success in deep learning. These are some of the experimental details. And so notably, to begin with, you can already see, even with MNIST, if you push things, a small gap between these. So this is error percentages. This is error percentages for MNIST. And so there's even a bit of a gap here, but people have been sort of kind of happy to ignore those because everything's within 1%. So it's sort of like, okay, 1% error. I mean, kind of who cares? So I should say, these are a bunch of variants. So from DTP down to DFA, these are a bunch of variants of more biologically plausible algorithms which do not have weight transport, right? So where you've removed the weight transport. This problem gets worse when you move to something like CIFAR. So here the gap really starts to show up. So actually, feedback alignment, I think, of the variants that we looked at, including different target prop, actually fares the best. But now there's about a 5% gap when you move to CIFAR. And this really comes to bear when we look at ImageNet. So these are cases where you need sort of like at least 5 or 6 or 7 layers of processing. You need a reasonable size network. And here the difference is stark. So these lines down here are variants of backpropagation. They're getting about 40%. It should even be said, this is using relatively small networks for what are used for ImageNet. And these guys up here, many of which are flatlining, are different target prop and feedback alignment. So this is when you move to really like much larger networks on harder problems. Yeah. Yeah, I think for the interest of time, I was kind of brushing past this point. There's kind of an interesting side note here, which I'll make very quickly since the question came up, which is that in this work, we also looked a little bit about this issue of convolutional networks versus untying all the weights. So basically you have the exact same structure, but you untie all the weights. And actually, it's not such a big deal. So this is to keeping the algorithm fixed, backprop, in both cases. you can see a small difference. LC stands for locally connected versus this guy is the real ConvNet. And so you do see a small difference in performance, but it's really pretty tiny relative to the differences we're seeing across these learning algorithms.
Right, but my question is, why is the number, which is 31.87%, so high? It seems like with convolutional nets and CFAR.
Yeah. Okay. So yes. Yes. So there's a couple reasons for that. Yeah. Your point is yes. So these are actually, this is actually pretty poor performance for backprop with a convolutional network. The answer here is that we used pretty small convolutional networks for a bunch of reasons that I am happy to talk about. The issue in some sense is that I suppose the real focus here was let's examine how effective these learning algorithms are, and therefore we're not picking like state-of-the-art architectures, right? I can get into the issues if you are interested, but that's the effective answer. That's like good eyes. Yep. Okay, so similarly, this will apply to the ImageNet results that I'm about to show you now, although I'll show you some nicer ones in a moment, I promise. Okay, so this was ImageNet, and you can see this. The results here are just stark. So all of these variants of difference target prop, some of the variants that we created of difference target prop and feedback alignment, their top 1 and top 5 errors are just abysmal relative to what you can get with backprop, right? So there really is. So I guess basically the message then is, although people have produced a bunch of algorithms which get rid of weight transport, and that seemed to be okay on sort of medium scale problems. For these harder problems, these are really breaking down. Okay, and so why is that? And it's worth reflecting on it for a moment. I told you about this sort of spectrum of credit assignment algorithms, and I drew it as one-dimensional. It was a bit of a lie, but it was a good way to get sort of think about this initially. It's probably better to think about it, better to think about these algorithms like this, which is that there's sort of some sense in which you can talk about variance, which and another axis here called bias, and backprop in some sense is the 0, 0. So it has, if you like, with respect to the full data set, no variance and no bias with respect to the true gradient. Node perturbation and weight perturbation, actually they have 0 bias, so they won't point. They, in some sense, on average, they will point in exactly the same direction as backprop. So they will, in the long run, go exactly in the same direction. They just have huge variance, and that means they're crazy slow, right? So you would need to sample many times that noise and make many updates to go in the same direction. Difference target prop and feedback alignment have this unfortunate issue that, in some sense, although they have low variance, they can and do, in fact, for those more difficult problems, have large amounts of bias, which basically means that ultimately they start recommending directions which are not congruent with backprop. So they just will not move in the right direction to minimize the loss, even if you run them longer. So I think actually what we're in the business of now is thinking more about this space. We want to be close to backprop and also sort of obeying biological constraints. But for the moment, we're literally dealing with one biological constraint, the one that maybe we've agreed on most, and seeing if we can make progress there. There's been some cool work commenting on this, actually, from the Poggio lab and from Larry Abbott's lab recently. You can think actually that maybe there's sort of maybe a spectrum here in terms of weight transport, where feedback alignment really has none, and backprop is full weight transport. I basically set B to be the transpose of those weights. And in some of this recent work, they looked at things like this, where they said, well, what if I just set B to just be the sign of the transpose of those weight matrix? So send far fewer bits, right? Send far fewer bits, or even just do this very occasionally. So just set that very occasionally, every epoch, say, to the sign of those weights. And actually, that does work. That does work significantly better. So if I'm not going to go into the details here, but what they showed is that they can get a big performance jump versus feedback alignment by sending at least a bit of the sign information on occasion. It still leaves us, though, with the question about, so there was still performance gaps versus backprop, and the transport of sign is still a bit mysterious. So in one of the papers, they suggest that maybe the sign concordance, the sign symmetry, could be set up in development using some precise circuitry wiring. I'm not sure. what I'm going to do now is suggest another alternative that we've been playing around with recently. So there's two of these approaches, and one of them I'm going to call weight mirrors, which is something we just played around with, which is that we are really going to have another kind of phase where we're going to directly learn transposes in what we call a mirroring phase. I'll describe what I mean by that in a moment, but basically we are going to have, again, a learning rule which governs the backward synapses, and it's going to be local, and that way we're going to sort of get transpose-like weight matrices, but without having to do weight transport anywhere. And the other alternative that we've looked at a bit was a suggestion from way back in the literature in 1994. This paper from Cullen and Pollock. I have no idea how to say those names. Unfortunately, I don't know if they're around. I'd love it if anyone could tell me if they know these people. So anyway, and they had a suggestion, which I think this paper has gone largely ignored, kind of for a good reason. So what they suggested was that if you, instead of so they said, okay, we don't want to do weight transport. We don't want to actually send the weights around. But what if we send the updates for the weights around? So that is, we compute the updates for the forward weights, and we sort of send them, to the forward weights and to the backward weights. And then we do a bit of weight decay on both those, so that initial conditions of those randomly instantiated weights will slowly drop out over time, and you'll be left with, in effect, the transposes. I'll try and make that a little more clear in a moment. The trouble with their proposal at the time, I think, and I think it has maybe 4 citations since 1994, is that they basically replaced the weight transport problem with the weight update transport problem, which is similarly bizarre. But actually, if you sit down and look at this stuff, you can construct like local Hebbian learning rules, which will accomplish what they sort of proposed pretty easily. So that's sort of what we've done in that paper. So, okay, so I'll first begin by talking about this idea of weight mirrors. And we sort of evoke the idea of having 2 phases. Maybe the second one could be during sleep, not attached to much. The first engaged mode is the sort of normal mode of running a network where you're doing a forward pass and doing a backward pass, and the updates look like this. So the B matrix shows up here, and is used to take errors or error gradients at this point back through the network, and then this is used to make updates to this weight matrix, say. Okay, so that's the normal sort of learning business. This is what we're suggesting in the mirror mode, and it's actually really simple when you sit down and just sort of ask, how would I get weight like transposes in my backward weights without having to transport that information around? How would I just learn those? And actually, the learning rule can look as simple as this. So that is, this weight matrix is just updated with a Hebbian-style learning rule like this. We do actually use and want weight decay on that, so it's something that says keep everything a bit small. But effectively, it looks like this. And the learning then basically goes like this. For this layer, you just activate it with noise, just independent noise. This goes up and over here, and then you send these signals here. So there's a set of neurons, I should say. There are a set of neurons which are in some sense constituting the backward pathway. You basically just run this update, and that's it. So to see that produces the desired effect, it's actually really simple. You can think about it like this. So this delta B that you make is looks like this in essence, and you can think about that as sort of this component of it. This is the learning rate. You can think about that as descending some loss function, right? So basically, you wrote down some loss function. You're going to descend it. You're going to sort of take the derivative with respect to B. And so what is the loss function? And I'm not going to show you the whole derivation, but you'll see very quickly that things will do roughly what we want. So let's just look at this. So here's my sort of expected value of x, y transpose, sort of where x was the stuff that I sampled from this normal. And then I just put that through, I put that through my forward weights. Just rewriting that, I get this guy. I can pull out the W transpose, and I'm left with this. And that's it. So basically, then the delta B, or B, is then integrating a signal which is proportional to W transpose. Right? So then what I'm doing then is just I'm driving B towards W transpose. I do actually need something like weight decay to keep it from running off, but it will go there effectively. The Collin-Pawlik update is similar in that I can sort of imagine having this backward pathway set up, sending activities back and forth between these neurons. But basically, at the end of the day, what does it look like in the backward path? It looks like a weight update that, again, is effectively just a Hebbian-like rule on what are locally obtainable signals. So in the end, you have these kind of funny symmetric things. You run a weight, this guy for your forward weights with a weight decay term, and this guy for your backward weights with a weight decay term. And the weight decay terms for the Collin-Pawlik really are crucial, because if you like, they've both been instantiated randomly. So if you make weight updates on these guys, even though they are in some sense the same weight update, starting from different initial conditions, I can run off into who knows where. But what's happening is that weight decay is pulling me back down toward the origin, and eventually you'll end up with effectively the same thing. Okay, so then what this looks like on properly, and someone was worried about the networks. So what this looks like in I would say proper large deep networks is this. So this is feedback alignment here. This is top one error on ImageNet. So this is feedback alignment, which really suffers in this regime. Sign symmetry is the one that I mentioned, where you're sort of transporting the information around, but only transporting the sign information. And still, as I said, there's a sort of fairly big gap relative to backprop in the end. And then both the weight mirroring and the Collin-Pawlik algorithms basically track backprop right the way through. So that is using local update rules that look like effectively Hebbian updates. I can create error pathways for myself, which in the long run can drive learning even on really complicated, really big networks. Just a little bit of diving into that. I can then go into these networks and look at that angle that I talked about earlier, this delta angle. And for sign symmetry, it's sort of, it comes down and it's there. The scale here is between 0 and 90, and you can see actually that the learning is really effective, given that this is just the sign information, and given that the angle to backprop, so backprop would be lying on this actual axis, given that the angles aren't that great, the learning is still pretty fantastic. And I think that's part of the lesson here, is that these things could be pretty sloppy, and you could still do pretty well. So this is for the weight mirrors. The scale here has changed drastically, so you can see these things drop way down and stay pretty low. So that's 25 degrees, which in a very high dimensional space is very low in a certain sense. And then the Collin-Pawlik rule really brings these things down and keeps them down like crazy. And I think it's important to say, probably this kind of fidelity of the backward pathways really would not be necessary. I mean, something in between these things may work just fine. So I think we can begin to have new algorithms that live in this space. We're beginning to play with that. There's lots more to do, I think, especially with respect to biological constraints. I think I'm wrapping up now on time. Is that right? Yep. I miraculously have I think maybe finished on time. Okay. So what do we? I think as a summary takeaway, I've been kind of obsessed with this part of this space of principles that we care a lot about in machine learning, and I think we maybe ought to care more about increasingly in neuroscience. And we know some things now. I mean, backpropagation or something like it, where I compute gradients rather than just estimating them, is really crucial for learning complex functions with deep networks. There just doesn't seem to be a way around that. So we need to approximate it in some sense. To make effective weight updates, the structure of the downstream function should be communicated back upstream. And there's lots of ways that could look, and we should dig into it. We'll see. Feedback alignment shows that this information need not be precise, at least in small scales. But really, we're just beginning to explore algorithms that perform well and match even the simplest known biological constraints. And there's tons more to do on that front. And really, we should come at this from both ends. So I think people in neuroscience who have experiments that sort of unpick, what are the kinds of computations that circuits can perform. We need to know more and more about that. And I think actually things are surprising us. They can do more cool stuff than we would have thought. It's not just Hebbian plasticity and that's it. And then from the other end, we need new machine learning algorithms that obey those constraints, but still perform well. And that's crucial. So, and this is kind of the end from which I've been kind of coming the last little bit. But it's really going to be a convergence of these things in the end that gets us anywhere interesting. And I'm going to wrap it up there. There's been a whole host of people who have been involved and with various aspects of the work I've shown you, and actually, huge amounts of the credit go to them. Thank you very much.
Okay, we do have time for questions.
Really nice talk, awesome work. I guess I wanted to hear more about the philosophy and some of the future directions that you kind of talked about. It seems that there's kind of two potential overall goals for this kind of work. One could be to build really fancy analysis tools that are really good at analyzing data.
Yep.
In which case you might want to just run with backprop and build huge networks and do really nice mysterious things. On the other hand, if you want to understand the brain, you might want to make those networks a lot more biologically plausible. And I think there's, you've got a bunch of work on that front, but there's a big way to go, in terms of cell type and cortical layer and all those
Yep.
kind of things. So I guess what's the goal and how do you bridge those two?
Yeah, on the first one, for doing experimental analysis, I mean, I don't see any reason not to play every trick in the book. I mean, you're doing engineering, so just go crazy, right? I mean, do whatever the machine learning, whatever works best. So I don't know if I have much more to say about that. I mean, do the best engineering you can, and pick up the newest techniques you can. On the second point, I think that there is a little more to say, which is that I think it's really so early on, we don't even have a sense of the space in some sense. But I was talking to Florian a bit about this earlier, we're starting to have tons of new data, connectomics, activity, and in some sense the question is what should we do with all that? And I guess what I would say is that I think we should use it, and I think that there is really contention about this, but I think we should use it to try and make inferences about those three things that I mentioned, which are basically the architectures, the loss functions, and the learning rules. And just to highlight why this is contentious, and that's what you should aim at, and why is that contentious? There are a lot of people who will feel like we're really missing something, and that is like, how do circuits compute what they compute? And in some sense, that's a bit left out of this. And that is intentional on my part, and it's because I think that's probably ultimately a bad route to go down. Okay, why is that? If I take one of these big deep networks that I've trained to do ImageNet, this thing's got some number of million parameters. And I think actually, ultimately, there is a lower bound on the number of parameters that you could hope to compress that thing into. And that lower bound is still large enough that I don't think you're going to be able to sort of pick up that object and have a nice intuitive feel of it as a human being. And so the question is, what are the objects which are compact, which are going to be compact enough that we should pursue understanding them, right? And I think that those things which are compact and which give us like the most leverage in terms of experiments, in terms of understanding, tend to be these. So when and certainly, like, to give you a hint of this, when I worked on AlphaGo, I mean, we spend a lot of time thinking about representations and so on in neuroscience, and I'll say there's in a sense a good reason to do that. But in that project, we feel like we have sort of, in some sense, a total understanding of the system, and we pretty much never looked at the representations. We did once, and I'll tell you what it is. But you'll see why it kind of makes it is a bit silly. So we basically, sometimes when these things aren't learning, when you go to a new computer hardware architecture, you're like, okay, what the hell is going wrong? It's just not learning. Then people went in and did a histogram of the activities and basically see that the like activation functions are saturating that. And that's the extent to which we care about the representations, right? So which is to say basically not at all. It's really these things, and maybe learning rules, maybe I also mean like an optimization procedure like MCTS, but it's basically these things that we want to write down. We believe that they're compact enough. And I think that this is a bit contentious. Like I think there will be a lot of people who would say, well, I don't understand, say, how those networks are doing what they do. I think there may be a sense, well, in some very direct sense, I absolutely know what they're doing. I've written down all the weights, I've written down the activation functions. It's like a total white box. And yet people remain unsatisfied. And I think, though, that that's going to remain. I don't think that we're going to sort of puncture that. And that's in some sense because the function which represents a good value function for Go, or represents, here's how to tell that this is a cat, those are terribly complicated functions which you're not going to be able to compress into an easily digestible human form. So to your question, I think what you should think about doing, my recommendation would be, yes, we have to record activities and look at representations, but you should be doing that to infer these things, because they're the things that are compact and about which actually give us like leverage.
So it seems like this weight mirroring stuff you're talking about at the end, if you took it really seriously, then Snake would make the prediction that in a network that was doing some kind of error-based learning, that there would be like a big asymmetry between using Hebbian learning and backwards connections versus not in forward.
Yeah, yeah, there probably is. You probably would make predictions like that, which would be great to go and look at. And I think I know little enough about it that I would make any prediction now. This is very new stuff that we've done. Yeah. I should say as well, when I said we are only beginning to even sort of have a sense of what the space looks like, I really mean that. I think there's a handful of people who have cared about these kinds of considerations, and beginning to connect this up to the real the real neuroscience literature is something that needs to be done a whole lot more.
So, that much all over the place in supervised, unsupervised, reinforcement learning. But what fraction, to your knowledge, what fraction of the sort of leading models now have anything like a passive weight decay in there?
I have weight decay. Weight decay still shows up a little bit. It's true that a lot of people just use other regularizers that perform in some sense as well or better, but it is less frequent. I actually think so. The AlphaGo networks actually did use weight decay, funnily enough. But actually, as far as whether it's used from application to application, weight decay is a bit, maybe in a sense a little passé. I mean, in any case, but I will say this. I mean, in the context of biology, there are other issues, right? So when, so although weight decay isn't used as much, things like batch norm are used like crazy, and batch norm has a lot of the effects in weird ways that weight decay would have. And so if you're dealing with biological signals where maybe someone hasn't normalized everything for you nicely, you need to keep things within nice ranges and so on. Maybe there's a lot more use for it. That's mostly conjecture.
Two more.
Yeah. There was one here and then.
So recently there were some attempts coming from John Hopfield's group in using kind of, purely Hebbian and local learning to learn a first layer of weights, and they demonstrate some nice performance. And I'd be curious to know what you think about this attempt.
To learn what? Sorry, I missed the second part.
So basically, like, so what was done, the first layer of the neural network was trained using Hebbian learning,
Yep.
without any great percent.
Yep.
And then the top layer was used using something like perceptron learning.
Yes. Yeah. Okay. So this is a very good point. I mean, in the sense that I think that there's a temptation, and I think it's a very good temptation. There's a temptation to hope that something like greedy layer-wise unsupervised learning, and then some supervised learning at the top of that, is going to be good enough. I think that so people have done all kinds of work like that in the past, and mostly people in machine learning just know it does not work well for hard problems. So it tends to work reasonably well for reasonably easy problems, and then it just scales worse and worse as you go to harder problems where you need more depth in your network. So that's the simple thing to say. I don't know about these particular results, but many people have looked at this in the past. I think I had another comment to that, but I've lost it, and maybe we're going to close up anyway. I don't know.
Very last one, was there one hanging?
Okay. Oh,
Sorry, there was one.
there was. Okay, it was before. Okay, I'll
I have a question about, so in backpropagation, a lot of people like have trouble tuning learning rates. And that seems like an interesting thing, kind of. I was curious in your slide where you showed these other methods that kind of track backpropagation. How are you tuning kind of the learning rates on these guys? And do you have any biological common predictions?
Yeah, that's a good question. So first of all, just to say very concretely, this was with a very small, simple grid search. That's how we tuned it. It was very like a relative. I think we searched like 5 different learning rates, and then there's a simple schedule that we're also using here, where you basically slow down learning twice. You can see the jumps, which is really like pretty standard. There's much more intelligent things you can do to a certain extent. Things like RMSProp and Atom do a great job of like tuning your learning rates for you. They tend not to give ultimately the very best performance, but they tend to work very well. And looking at sort of analogs of RMSProp or Atom would be like a very cool thing to do. I don't know if anyone is or. Yeah.
All right, let's thank our speaker once again. Really wonderful. Thank you very much.
Thanks for having me.
You know, a couple people and then Sage will come and get you, I think, for lunch. Which maybe should be quick, and I'll see you.
Okay, great. Thank you.
I was doing a lot of everything. I just want to mention about, you mentioned issue of bias. That was factorable for any kind of network bias. You also mentioned about the realistic neural model. Is there any chance that, of course, there will be maybe when you incorporate some particle constraints, there will be some kind of bias in the learning. And so maybe, hopefully, if the network architecture and the learning might be aligned together,
Yes.
such that
It's at least small bias. At least you want the bias to be very small.
so maybe for a certain network architecture, maybe the bias doesn't matter.
Right.
That's
But
wishful
for other-
thinking.
right.
But then